The Milky Way galaxy is home to billions of stars, many of which are larger, brighter, and hotter than the Sun. Stars exist in a wealth of different varieties, which drive their unrivaled sizes, with the scale ranging from stars the size of Jupiter to stars larger than Jupiter's orbit around the Sun. You've likely all seen pictures of the latter, various giant stars which completely dwarf the Sun, rendering it as nothing more than a grain of sand next to a beast of the cosmos. But how do we arrive at these conclusions? How do we measure stars to identify these mind-blowing sizes? And above all, which of them is the biggest? A star is a massive, luminous sphere of mostly hydrogen and helium in a plasma state, a kind of ultra-energetic soup of free-roaming atomic nuclei within a sea of electrons. Within the core of a star, atoms are under so much pressure from the body's gravitational influence that they are undergoing nuclear fusion, whereby the nuclei are stripped of their electrons and crushed into one another, combining to produce heavier elements. For most of a star's life, hydrogen atoms are fused into helium atoms, like in our Sun, which converts some 600 million tons of hydrogen into helium every single second. This process generates an incredible amount of outward pressure, which is counteracted by the star's gravity, keeping the body held together. So essentially, a star is a giant, continuous explosion. But how does this explosion start? Well, to make a star, the first thing you need is gas. Stars form inside gaseous clouds containing large amounts of neutral hydrogen and helium, which are two of the most abundant elements in the universe. Within these gas clouds, gravity attracts suspended atoms together into clusters over a very long time. Pockets of denser gas gather and then fragment within the cloud, drawing in more atoms until the pocket starts to undergo a gravitational collapse, whereby the atoms compact tightly enough to begin raising the temperature at the core of the cloud. Eventually, the atoms at the centre are so tightly compressed that the pressure and energy strips off the atom's electrons, creating ions, and the exposed hydrogen nuclei begin being crushed into one another, thus igniting the star's fusion plasma furnace. The fusion in the core of the star forces the plasma outwards, increasing the star's size. However, the body itself has gained so much mass that it is generating an enormous gravitational influence, lugging the plasma back in towards the centre. These inward and outward forces counteract each other, before settling into a fragile balance of hydrostatic equilibrium, where gravity and radiation pressure are in equal measure. The edge of the star where this balance is struck is marked by the photosphere, the outer surface from which light is emitted. This is the edge we use to determine the star's absolute radius, and thus its size. When comparing other stars, the value is often given in solar radii, a unit of measurement equivalent to the radius of the Sun, about 695,700 kilometers. This serves as an effective way to grasp the bewildering sizes of the largest stars. The size of a star depends largely on its mass, and a number of factors affect how massive a star can become, particularly the amount and composition of star-forming gas from which it came. However, there is thought to be an upper bound limit. For example, you wouldn't find a star as large as a galaxy because it wouldn't be able to keep itself held together. The energy output of fusion at the core of a star scales with the star's mass, and so if a star is too massive, then the fusion will be too energetic, and gravity will not be able to hold on to the star's structure as it blows itself to smithereens. Similarly, molecular clouds from which stars form need to be a certain mass, density, and temperature in order to collapse and begin star formation. When gas clouds collapse, pockets of greater density fragment from the global structure of the cloud. So instead of a gas cloud thousands of times the mass of the Sun producing one hypergiant star, it is more likely to produce hundreds of smaller ones instead. With these constraints in mind, old theoretical models have suggested size limits of around 1,500 solar radii for the largest possible stars, so that's 1,500 times the diameter of the Sun. That is a size difficult to comprehend, but what's even more surprising is that since then, we have discovered a handful of stars which seem to sit well above this incredible benchmark. So how does a star become this large? After a star has formed and its fusion burning is underway, it enters what is known as its main sequence, with the hydrogen in the core of the star gradually being turned into helium. Depending on the mass and composition of the star, this main sequence burning phase can take anywhere from a few million years in the most massive stars to billions of years for more stable stars like the Sun. However, stars do not vary that greatly in size during their main sequence. The main stage hydrogen burning is the coolest and thus least energetic kind of fusion that a star will undergo, and so does not produce as much outward pressure as other kinds. It is only when a star begins fusing elements heavier than hydrogen within its core that it enters a much larger and more energetic phase of its life. At the end of a star's main sequence, all the hydrogen within the star's core has been exhausted and fused into helium. Helium fusion requires much higher temperatures to occur, and so initially the outward pressure produced by the star lags, tipping the balance of the forces in favour of gravity, causing the star to contract and shrink. However, as the core contracts, more matter is pulled into the centre, compressing the core further and heating it up again. Meanwhile, gravity pulls the precious little hydrogen remaining in the outer layers of the star further in, towards the area of the core which is hot enough for hydrogen fusion. This leftover hydrogen then wraps around the helium centre in a shell-like structure, within which fusion resumes. The outer layers of the star then begin absorbing the majority of this energy, causing the star to balloon in size to tens or hundreds of times the size it was during its main sequence. When this happens, the surface area of the star greatly increases, spreading the energy release more sparsely across the surface. This causes the star's surface temperature to fall to between 3000 and 5000 Kelvin or so, and appear redder. The star has become a red giant. Thus, the surface temperature of the star falls, but inside the core, the temperature again begins increasing until the star reaches the threshold at which the all-helium core can be fused into carbon. This significantly increases the energy output of the fusion, causing the star to swell up even more. In about 5 billion years or so, the Sun will eventually exhaust its hydrogen fuel and follow this process, expanding to over 250 times its current diameter, engulfing Mercury, Venus, and probably the Earth as well. However, our Sun is only a medium-mass star, which places limits on its fusion. When the Sun has finished fusing helium into carbon, it will not be able to reach the temperature required to fuse anything heavier, and will become unstable, initially growing larger, but ejecting around half of its mass into a surrounding nebula, before becoming a small white dwarf star. In contrast, stars much more massive than the Sun can reach the compression levels required in their cores to fuse the carbon left over from helium fusion into heavier elements still, like oxygen, sulfur, and even silicon. This generates even greater outward pressure, allowing the largest giant stars to expand to billions of kilometers in diameter. This is how stars become truly huge in the twilight of their lives. Red supergiant and hypergiant stars are the largest type of star we see in the galaxy, with some so large that they could engulf our entire inner solar system within their photospheres. To determine a star's radius, we need to know two key pieces of information. One, which we can directly and easily measure, is its angular diameter. That is, the size it appears when viewed from the Earth. The second, and much more elusive value, is its distance from Earth. When we know the two, we can scale up the angular diameter and we have our star's actual size. But this is easier said than done, as it is very difficult to calculate stellar distances precisely. Even with space telescopes, most stars appear as nothing more than tiny, featureless dots of light due to their immense interstellar distances, and also due to interstellar radiation, which hampers the light as it travels towards Earth. There are also other problems. For example, many of the largest red giants and supergiants are unstable and expel large amounts of material into their surrounding space, creating nebulae, dust bubbles, and even radiating torus-like structures which obscure the star within. And, unfortunately, a great many of the stars in the Milky Way galaxy are impossible to see altogether. The light from the Milky Way's core drowns out a large number of stars within the densely populated heart of the galaxy. And similarly, the dark, dusty clouds along its arms block out large swathes of outlying stars. In short, it is impossible to say what the largest star in the universe is, or even the largest star in the galaxy for that matter. But nevertheless, we have managed to identify our fair share of contenders. Fortunately, for the stars that are large and local, their distances can be calculated directly using a form of triangulation, also known as parallax. As shown in this demonstration, when moving from side to side, objects in the foreground appear to be moving faster than background objects, and we can apply this phenomenon to the stars. As Earth orbits the Sun, its position changes every half year. And so, if we record the viewing angles of a star every 6 months, we can use some trigonometry to work out the distance based on the two positions. In practice, this may not be done with visible light from a star, but rather through very long baseline radio emissions, which are produced by masers, random spectral emissions generated by a star's atmosphere. Parallax allows us to measure interstellar distances with a great degree of accuracy, but it only really works for nearby, large, and luminous red giants. For smaller or more distant stars, the displacement of the object's emissions against the backdrop of space becomes too subtle, and standard parallax techniques have margins of error too large for the estimations to be meaningful. As such, we can only survey stars through parallax measurements accurately out to a distance of about 400 light-years. Not a very useful sample size when trying to find the largest star in the galaxy. However, all is not lost. There are other means to determine the distance of a star, albeit indirect means. But because we have a selection of nearby stars that we can measure precisely through parallax, this gives us a dictionary of known stars whose well-understood properties can be used to deduce the characteristics of more remote stars. By comparing the spectral data of distant stars with the spectrums of stars whose properties we know, we can estimate the two things we need to find the radius of the star: the luminosity and surface temperature. A star's luminosity is its intrinsic brightness, not how bright it appears from the Earth, but rather a measure for the amount of electromagnetic energy that is being emitted in watts. When dealing with other stars, we measure this in terms of solar luminosity, the energy output of the Sun, given by the International Astronomical Union to be about 3.828 times 10 to the power of 26 watts. Because the most remote stars are too far away to take direct spectral measurements, astronomers instead take measurements of the star's emissions at different wavelengths, and then reproduce a spectrum that would best fit the data recorded. Once we have recreated our spectrum, by measuring the width of certain absorption lines, it is possible to assign a spectral class to the star. The luminosity and temperature we can then infer from known nearby stars of same spectral type. Certain spectral types are indicative of cooler red giants, with surface temperatures of around 5000 Kelvin or lower, whereas other types are indicative of hot blue stars burning at tens or hundreds of thousands of Kelvin. In truth, there is a lot of guesswork, and there are a number of variable factors which make some data harder to predict. But once we have estimates for the luminosity and temperature of a distant star, we can apply these values to the equation used to deduce stellar luminosity based on the surface area and temperature of said star. By doing a bit of algebra, we can extract the radius from the surface area and rearrange the equation to solve for the radius of the star. And finally, with all these values plugged in, we arrive at an estimate for the star's size. So with all that said and done, what are the largest stars that we've found? For a time, it was thought that VY Canis Majoris was the largest star. Canis Majoris is a red hypergiant, oxygen-rich, pulsating variable star located in the constellation of Canis Major. Its distance is thought to be around 3,900 light-years from the Earth, and it is thought to be located either within or slightly in the foreground of a large molecular cloud known as SH2310, one of the largest star-forming regions in the Milky Way, and consequentially home to many giant stars. Canis Majoris is the largest and brightest of them all. It is extremely luminous even for a red supergiant, owing to a heated disk or bubble around the star which gives off a high infrared excess. The star was first noted as early as 1801, and it continued to be observed throughout the century. By the start of the 1900s, it was accepted that the star was an extreme object, and during this time, astronomers had noted no less than 6 distinct bright patches around the star, leading to the hypothesis that it may be a binary star system or even larger. By the end of the 20th century, it was known to be a post-main sequence red supergiant star, and we now know that the bright components observed are part of a highly reflective surrounding asymmetric nebula, caused by explosions and jets from the star's photosphere. Canis Majoris is in the final stages of its life, and it is losing a lot of its mass as it fuses oxygen and other heavy elements within its core. Much of the mass ejection is thought to have happened fairly recently, within the last millennium or so, and it is indicative that the star does not have long left before it goes supernova. Estimates of the star's size have varied over the decades due to its uncertain distance, and also due to the fact that it is a variable star which changes in size as it pulses. Studies in the late 90s suggested a distance of around 1,800 light-years, thus implying a smaller radius. But more recent and accurate studies have yielded distances closer to 4,000 light-years. In 2006, and then again in 2007, it was estimated to be somewhere in the region of 1,800 solar radii, making it a hypergiant star as well as the largest known star at the time. Today, its radius has been more accurately measured to be around 1,420 solar radii. But even at this size, it would be sufficiently large as to engulf the orbit of Jupiter, some 750 million kilometers away from the Sun. Of the few stars that are believed to rank above Canis Majoris, Scuti is probably the most well known, spending much of the last decade as the largest known star. Like the former, Scuti is a pulsating variable red supergiant star, which is located in the constellation of Scutum. It is not visible to the naked eye, and even appears faintly to telescopes, due to its location within the Milky Way's zone of avoidance, the section of the galaxy whose stars are obscured by the light from the galactic core. In addition, the star pulses every 2 years or so, and is shedding much of its mass, making accurate estimations difficult to constrain. In 2013, Scuti's distance was estimated to be around 9 or 10,000 light-years away from the Earth, yielding a mind-blowing size of around 1,700 solar radii, give or take about 200 to account for margins of error. Like Canis Majoris, this size is enough to engulf the orbit of Jupiter when placed at the centre of the solar system, and photons travelling at light speed would take around 7 hours to travel along its circumference, compared to the 14.5 seconds they would require to circle the Sun. Like many other supergiant stars, Scuti is shedding a lot of its material and blasting away its outer layers as it fuses heavier elements within its core, and inevitably it will go supernova soon. Because of its location deep within the galactic disk, it may be a metal-rich star. If this is the case, then instead of going supernova by fusing iron and collapsing, it may instead reach a hotter temperature before death, possibly evolving into either a yellow hypergiant, luminous blue hypergiant, or perhaps a Wolf-Rayet star, a kind of very hot and very volatile star with a high metal content. In all three cases, the star will produce strong, eruptive stellar wind emissions, so powerful that they will blow the outer layers of the star away and expose the core, causing a much brighter and more violent kind of supernova. However the star ends its life, it spells bad news for any planetary system orbiting the beast. Like the Sun, Scuti may have a system of planets, many times larger than the solar system due to the star's tremendous size. Scuti's habitable zone, the distance from the star at which water could exist on the surface of a planet, is thought to start at over 600 astronomical units away from the surface, which would mean any life on a planet like this would experience seasons that lasted for millennia. In reality, it is unlikely that anything is around to witness the star up close, as the constant ejections of mass and radiation from Scuti's dying breaths will have rendered all but the most remote planets uninhabitable. The star's eventual supernova would send this planetary system into further disarray, likely obliterating most of the planets and perhaps ejecting very distant ones on a trajectory out of the system, casting them into the wilds of the galaxy as starless rogue planets. In 2018, data from the ESA's Gaia spacecraft re-evaluated Scuti's distance using parallax measurements, giving a much lower distance of around 5,000 light-years, which would correspond to a radius of only 755 solar radii. Still enormous, but not big enough to be record-breaking. However, as we said earlier, parallax measurements are less reliable for the very distant objects, and until further tests are done to validate the finding, this lower distance and thus lower radius for Scuti remains tentative. Scuti was the king of stars for many years, but after the Gaia data release cast doubt over its true size, the throne was once again opened for a new stellar champion. And though there have been a few proposed stars with larger diameters than Scuti, one stands out as by far the largest beast discovered to date. Enter the latest and new largest known star, Stephenson 218. Stephenson 218 is located within the constellation of Scutum, the same as Scuti but lying significantly further away, around 19,000 light-years from the Earth. It lies within a densely populated star-forming region, home to several massive open clusters, each containing their own enormous red giant and supergiant stars. RSGC2, aka Stephenson 2, is one such open cluster, estimated to be around 20,000 light-years distant, and containing more than 24 red supergiants. Stephenson 218 lies within this area, and it is the brightest star among them, but it was not initially considered to be a member of the cluster due to its outlying position and also its abnormally high luminosity when compared to other cluster constituents. However, a later study concluded that the star was perhaps part of an outlying group of stars to the cluster, which is thought to lie at a similar distance to the rest of it. Thus, Stephenson 218 had its name assigned as a member of the cluster. However, it stands out from its neighbouring giants, being both significantly larger and more luminous than its surroundings. Assuming that the star lies at a similar distance to the rest of the cluster, then its luminosity is thought to be around 440,000 times that of our Sun, far above the theoretical luminosity limit for most stars, which was once believed to be around 320,000 solar luminosities, corresponding to the 1,500 solar radii size limit we spoke about earlier. But by applying Stephenson 218's observed properties to the luminosity formula, they correspond to a staggering radius of 2,149 solar radii, making Stephenson 218 by far the largest star discovered yet, and the first whose photosphere, when replacing the Sun, would be capable of engulfing not just the orbit of Jupiter, but the orbit of Saturn as well, which lies almost 10 times further away from the Sun than Earth does. This corresponds to a volume of almost 10 billion times that of our Sun, and it's hard to appreciate just how large that truly is. But what is even more bewildering is the fact that it may get larger still as it ages. Stephenson 218 is thought to be a relatively young star, and the older it gets, the hotter it will burn, perhaps swelling further and evolving into a yellow hypergiant before it goes supernova. In any case, it is considerably larger than both Scuti and Canis Majoris, and is by far the largest known star in the local group. Over the years, we have continually found larger and larger stars, and so it's reasonable to assume that something else will come along and knock Stephenson 218 off the top of the list before long. But make no mistake, it will take something truly remarkable to knock this monster off its pedestal as king of the cosmos.